Good afternoon. I always love to do this. Good afternoon. Welcome to our Artificial Intelligence lecture series, named after Raj Reddy. As you know, Raj founded the Robotics Institute, the Institute for Software Research, and many, many other things that define who we are today as the School of Computer Science and Carnegie Mellon University. So first, join me in thanking Raj for his service to CMU. Thank you. Now, in this lecture series, we talked about computer vision the last time, speech before that, deep learning before that, and today we're going to talk about outdoor autonomy. And for that, I am delighted to introduce our speaker, Professor Raquel Urtasun. She's the founder and CEO of Waabi, an AI company building the next generation of self-driving technology. She's also a full professor in the Department of Computer Science at the University of Toronto and co-founder of the Vector Institute for AI. She has made numerous contributions in computer vision, machine learning, robotics. By the way, as a side note, I was talking to Raquel this afternoon, and don't think that those two things, the industry thread and the academic thread, are disjoint. In fact, she told me she has 15 PhD students currently, so she's doing an amazing job at combining the two. Raquel earned a PhD from the Computer Science Department at EPFL in 2006 and did a postdoc at MIT and UC Berkeley. In 2024, she was named a Fellow of the Royal Society of Canada for contributions to computer science. She was included in the CNBC Women Transforming Business list. In 2023, she was named one of Time's 100 most influential people in AI, made Business Insider's AI 100 list of top people in AI, and was awarded the Ontario Chamber of Commerce Emerging Tech CEO Award. And this is the one I like the best. She was also awarded the Order of Ontario, the highest civilian honor of the province. Please join me in welcoming Raquel.
Thank you, Marshall, and it's really a pleasure to be here today. And I think last time I was at CMU, I think it was 2008 or something like this. So it has transformed and changed, significantly. It's amazing to see all the progress that is happening here. And for those of you that you don't know this, my academic connection to Marshall is, if I'm not mistaken, he is my academic uncle, right? Since you're... Yeah. Since, I guess, her PhD advisor and my PhD advisor are the same. Cool. Anyways, so today I'm going to be, talking about, the road to autonomy and how to bring generative AI to the physical world and all the really exciting things that are happening at Waabi. So let's get started. So I think in this room, probably everybody's familiar with the term generative AI, right? It's this idea that we can build a system that is able to generate, an AI system that is able to generate new content, whether it's videos, whether it's images, text, etc. And, over the last two years, this has had a tremendous impact in the world. And the idea of the system, with large language models, for example, is extremely simple. It's this idea that you have a very large corpus. You can actually learn very complex representations by learning to predict what is the next word in a sentence, right? Something that is, unsupervised, no human interaction, but enables you to actually learn representations that you can use for many, many different tasks. And that's why this type of model is called a foundational model. Now, if you look at the impact that this technology has had and is about to have even further, it's amazing. And no matter which metric you look at, it's off the charts. One of my favorite metrics is the one that you see here in the screen, which is the time it took, for different companies to reach 1 million users. Right? 1 million users is pretty big. So, Netflix, I'm sure most of you utilize one of these services, 3.5 years. Facebook, 10 months. ChatGPT, 5 days to reach, 1 million users. And I think that the latest projections for the quarter, if I'm not mistaken, is 250 million or something like this, right? So amazing, right? But if you look at, any other metric, it's very, very similar. Now, if we look at now what has enabled really this revolution of generative AI, is also very simple. It boils down to three different things. There is the availability of data that today we have access to the internet. A lot of our content is digitalized. There is at the same time the use or the new generation of compute that enable us to actually do a lot of computations in a fraction of a second. And it's not by chance that actually NVIDIA is, I think today, the most valuable company out there, right, with 3.5 trillion or something along those lines. And the last bit is there has been also some fundamental algorithmic contributions over the last couple of decades that enable this to happen as well. And my friend and colleague Jeff Hinton just got the Nobel Prize for this, which has been amazing to see. Nobel Prize in Physics for computer science and for AI. So if you look at, this is all great, digital world is transformed, fantastic. The next thing to think about is what is next? What is the next frontier that we're going to see over the next 5, 10, 20 years? And to me, it's very clear that this is actually the impact that this technology is going to have in the physical world. We don't have windows in this room, but if you look outside, your window, you don't see robots today. But this is going to be something that is going to be changed over the next 10 years, where they're going to be everywhere. And this type of technology is going to be fundamental to really build scalable solutions to be able to provide something that we can use everywhere. Now, if you think about the idea of I want to bring generative AI to the physical world, there is three different challenges or properties that you absolutely need your system to have, that in the digital world, you can get away without paying maybe too much attention to it. These three properties are the following. The first one is generalization. Why is this important is that we're going to build physical systems, whether it's self-driving cars or other types of robots. So they're going to be interacting with humans, and their mistakes have catastrophic consequences. So no matter what they are exposed to in the world, they need to be able to do the right thing. Right? So they need to generalize to things that probably they haven't seen before in a way that they're able to safely act in the world. So if you look at the images over here, they look like very rare cases and whatnot. And every time I show these images, people always tell me, like, yeah, Raquel, these are things that you will never see in a lifetime. Well, it turns out that I actually took 3 of those pictures. Okay? And I have so many on my repertoire anyways. So these rare cases are everywhere, and there is many, many, many of them. So that's one property. They need to generalize. And large language models, they do a lot of memorization today. Right? So that's not sufficient. The second one is that the systems have to be very, very efficient. They are going to run embedded in the robots, right? And these robots should consume little energy, right? So we need them, to be much more efficient than your typical large language model kind of inference algorithm. And I will argue that the efficiency is not just about running on the vehicle, but also it's very important that we move from where we are today to a sustainable AI future. Okay, so also the way that we do training needs to change significantly so that we can train these algorithms extremely efficiently as well. Otherwise, we're going to look in terms of a battle for power and potentially destroying our planet. Okay, so very, very important that we build very efficient algorithms for training as well. And the last bit, which will not surprise anybody, is that we need to build these are safety critical systems, so they need to be safe. But being safe is not sufficient. That probably surprised you, right? Why I say it's not sufficient is that you need to be able to prove that they are safe before you deploy, right? So that provably safe is something that is a must for really deploying the systems in the real world. And as you can imagine, just a standard generative AI technology is not satisfying these 3 properties. All right, so over the last many, many years, I've been looking in kind of like developing this type of technology that will be able to satisfy these 3 properties. And today, I'm going to go a little bit deep in some bits and pieces of what we have built. Now, when I started the company, this idea of generative AI for the physical world was something that we could use for any form factor. right? We could do humanoids, we could do drones, we can do warehouse robotics, self-driving cars, whatever, right? And I decided that trucking was really the right application. And the reason why is also pretty simple, which is that, from the economic opportunity is tremendous, right? Yes, in the US alone is almost $1 trillion opportunity. But at the same time, the industry is ripe. The customers really need this technology in order to really have, exploit the full power of their businesses. There is an acute driver shortage. Humans don't want to be truck drivers, particularly long-haul truck drivers. The conditions that you have of life are, I call these jobs very unhumanized jobs, right? They go weeks at a time on the road, and oftentimes they don't even have access to bathrooms, to showers, etc. Humans should not be doing this job. We should be doing better jobs. Safety, despite all the advances in ADAS systems, there is still many accidents and many deaths on the road, as well as the environmental impact. 20 to 30% of the loads of the miles that are driven by trucks today, the trucks are actually empty, right? So with robots, we can optimize that supply chain much better. From a customer perspective, you're probably thinking, like, why do I care about self-driving? Why I continue with my business? So there is, a very clear advantage, clear ROI. You can actually have much cheaper transportation, much more reliable, and you can utilize your trucks 3 to 4 times more. And the reason for this is that as humans, we need to rest, right? We have hours of service, and typically a truck is only utilized 6.5 hours, right? So you can go, almost 4x in terms of the utilization of your assets. So a tremendous opportunity to build also a more sustainable future there. All right, so the use case is ripe. This is great. So where are we today? So if you look at, there hasn't been a single solution or product. There is nothing available out there in the market. And if you look at the technology that has been developed for solving this, this task, has been what today we call in the industry AV 1.0. And this AV 1.0 is a very hand-engineered approach that is actually, very capital intensive. Is very where you build software stacks, for example, that are very brittle, very large. You need thousands of people. Where it's really, you need to encode all the prior knowledge into that stack for that system to actually handle or try to handle situations. And typically this is paired with, I need to drive millions of miles on the road to see what is the next set of corner cases that I need to solve. So this is an extremely painful, very labor-intensive approach that I call it a very kind of robotics mindset. And I don't mean that in a bad way. I mean in the sense that, when you're a roboticist, you are trained you have a large system that you want to decompose into small sub-pieces. You want to solve the sub-pieces, and then it will bubble up into a system. That's kind of your mindset. Versus an AI-first approach is a mindset where you go with, I want a single AI system that is able to solve everything, right? So like the polar opposites in terms of how you tackle this task. So that's where we are today. And when I started Waabi 3.5 years ago, I saw a tremendous opportunity to do something very different from what was available on the market, which is, why don't we have that AI-first approach and then trying to really unleash the full power of AI so that a single AI system can do all the tasks necessary for driving. And this was not something that I had the aha moment over time or anything like this. I spent the last more than 2 decades building this concept of the single AI system that is able to reason like humans do. And this is something that is very powerful because if we can build systems that can build abstractions of the world and understand what they sense, and then use those to reason about what are the possibilities and which ones are safe, then we should be able to build systems that generalize much better, that are very efficient, and they are provably safe because those abstractions can be interpretable. Okay, so that's kind of the concept of that we build, for Waabi and our virtual driver. So in order to put that into practice, we developed several generations of foundational models. Okay, so In the large language model domain, what you have is that you learn representations by learning to predict the next word, right, given the current sentence that you have observed. In the physical world, or in the case of robotics, you can predict your observations that you're going to see in the future from the past and current observations. Okay, that's kind of the analogy. But now, instead of discrete, you have a continuous problem, okay, where you try to predict multiple sensors, not just one word. So you can build this generation of foundational models, and today I will just touch upon two of the generations so you can get a flavor of how different they are and the kind of designs that we have. Okay, so this is the small part that is actually for maybe the AI, enthusiasts in the room. All right, so the idea is that we want to have a foundational model of the 4D world, right? And why is 4D? Because it's three-dimensional as well as in space as well as time. And we're going to build something that kind of mimics how, again, large language models do. So they work on discrete representations, which are words, right? The tokens. And in our case, so what we build is specialized tokenizers that take the the continuous observations from the sensors, and then they kind of represent them with a high-dimensional discrete space. Then you can build your word model, which is basically conditional on your actions. You want to predict how that's going to be evolving, and then you use a renderer in order to get back to the observations. So it's it's a little bit more complex, kind of the how you build the foundational model here than what you have typically in a large language model, which is just a big transformer, right? Which actually is built here with everything that we learn about building representations from sensors, as well as simulation through this renderer. Okay, and in terms of the discrete representations, so that you get a sense of this, it's very simple. Is that you can just divide your special observations in terms of a grid of tokens, and that evolve over time in order to get your predictions into the future. Okay, that's kind of the analogy, which is one more dimension compared to what you're typically used to. All right, so it turns out that this type of foundational model already work much better than what was available, out there in terms of, for example, predicting observations into the future. And this is comparative to some of the work that Deva and team have done here at CMU, which was a very, very exciting and interesting work, kind of pushing that leader generation in the past. Cool. So that worked really, really well, and it was, very interesting. However, there were some challenges, or it was not something that we could use really directly in terms of the self-driving task. So the challenges were that we have this continuous and high-dimensional sensor data that, although we discretize with tokens, we didn't get yet representations that were super, super accurate. So we weren't very satisfied with it. The second bit that we didn't like is this idea that can we make the foundational model learn representations that are, represent more of the semantics without explicitly hard-coding them for a self-driving vehicle. So we actually built a second generation that was very, very different, and I really, really love this work. And the idea here was that we are going to build intuitions from the physics of the sensors in order to build better ways to represent to learn these foundational models. Okay, so this is what a LiDAR observation looks like, which is basically these points that you shoot a ray, and then the time it takes to come back, roughly it represents where it is in the space. Okay, so you get these very sparse 3D representations that we can use to learn our foundational models, right? And so you can build actually loss functions that are utilize the physics of what the sensor is doing, and it's very, very simple. So the idea is that for every ray that you can shoot, right, if actually you see an observation, it means that you have hit an object. Right? That's clear, right? If it's turning back at that distance, it means that there is something there. But it turns out that there's more information than this, which is that the space between where you are and where you hit an object, since nothing returned, it means that there was nothing there in the first place, right? So you have these positive returns and these negative returns that you can utilize. Very, very simple concept, But by changing the way that you train these foundational models to try to predict this, instead of trying to predict the observation itself, made a whole lot of difference. And by doing this across all the rays and all the observations of LiDAR, you actually can build really exciting representations of the scene. Okay, so let me show you this with a video. All right, this works. Cool. So if you build this type of foundational model, what is implicitly learning is this concept of objects that are moving in space and time, and it's also learning implicitly the concept of uncertainty. And this was surprising to me that it learns to complete shapes and other things that have been traditionally very, very difficult for computer vision algorithms. And all based on just purely unsupervised learning with the loss function that I showed you before. So this was, mind-blowing to me that we could actually do something like this with this type of representation. And then there was some other intricacies in the way that we designed the system so that for the first time, instead of having explicit representations that are very, very expensive for time and compute, we are to actually build implicit representations so that the reasoning module can query where in space you want to get information. And that's a very powerful approach because with these implicit representations, you have infinite resolution. So you're actually able to get like super precise shapes if you train this with enough data and enough compute. So you can use this to inherently discover the concept of objects, how they move over time, etc. You can utilize it to forecast, so nothing was lost with respect to the previous model. You can actually render later. And you can also retrain it to do things like semantic occupancy forecasting and things like this that are traditionally used for self-driving vehicles today. So this foundational model, you can fine-tune it and do all the tasks that a traditional stack does today with very, very little data. So I'm going to show you some videos on the unsupervised piece, and then I'm going to show you some stuff in terms of semantics. Okay, so on the left-hand side, you see a perspective view from the top, first-person view on the middle, as well as a camera view. And as you see, is really understanding this concept of how things move in the world, and maybe where you don't see enough, and there is uncertainty maybe on the shape of that object or how it's moving, etc. It can actually handle tiny things like cones, things like this. And it's pretty precise. So we have a super resolution version of this that can get like really, really sharp on the edges, for example. It can handle unknowns in the world. As you see here, we were just driving around, we see a couch on the road, and it can discover that object and being able to precisely localize where it is in three-dimensional space and complete all the shape. So you can use, in self-driving, one of the things that is difficult is understanding things that you don't know what they are. With this kind of foundational model, you get all that for free. And then we look at comparison, in terms of some of the tasks available out there, and this type of model really works extremely, extremely well. And what was very exciting is that, as I said before, we can fine-tune it for other tasks. For example, if you want semantics, we can actually have very accurate bird's eye view representations by just fine-tuning the model to be from 3D to be two-dimensional and having semantics. Okay, so this is a little bit of the same that with large language models. You can fine-tune to do summarization, to the question answering, to be a chatbot, etc. You can actually fine-tune this model to do whatever you want your self-driving vehicle to think or reason about. And as you see over here, with just a few examples, actually gets the semantics really, really well compared to other approaches out there. Cool. So what I talked about so far was about this scene interpretation kind of model, right? And we can build this, several ways or generations of foundational models that enable us to discover how the world looks like in a way that we can actually predict that future. Something that, prediction systems are very important for self-driving. And now we can take those very rich representations and utilize them in order to reason about what all the possibilities that the self-driving vehicle can do. We can reason about what is the consequences of every action, a little bit like rollouts in the future, like you will see with a simulation system. And then we can train the system end-to-end, the entire thing, to actually do the task of driving in a way that is, you have the interpretability, so you can prove the safety, and then you have the guardrails and everything that you need in the entire system, well, all being learned from data in a single click. Right? So you get something that you don't get with the black box of some of the other companies. You get the best of both worlds. The advantages of some of the things that you get with the traditional approach and the advantages of a pure data-driven approach. So you can learn very complex concepts and you don't need to inject all those things for the system to handle them. So this actually turned out that work extremely well in practice. And yes, so that is clear. So it contrasts the end-to-end approaches that you will see with Wave, with Tesla, that are just this black box architecture, which is very, very hard to validate and verify the system. All right, and where you need, massive amount of data in order, fleets of vehicles everywhere in the world, in order for the systems to learn to do reasonable things. Cool. So that's as it relates to the brain of the self-driving vehicle. And I also wanted to demystify one thing, which is, oftentimes now there is this camp of, I have an end-to-end model and I don't want to use high-definition maps. And I have a traditional approach and I want to use a high-definition map. Those two things are not related. You can use, high-definition maps with, an end-to-end model. It's just, for us, we use them and they are used as a sensor. And what do I mean as a sensor is that they might be wrong. They might be construction. They might be a shift of the lanes, etc. So you still need to, be able to do online mapping, but you can utilize your prior knowledge as an additional sensor as you're driving in the world. And that's the approach that we took in terms of, how to, be robust with high-definition maps and at the same time be able to have the freedom to, handle constructions and other things. Now, one of the reasons why high-definition maps, people want to stay away from them is because traditionally they have been extremely costly, right? If you use a provider of HD maps, they're going to charge you around $1,000 to $2,000 per mile, right? Take it or give it. So what we built was also generative AI technology that enabled us to actually create these maps automatically. And if you can do this, then you can just use a final human for QA that basically just fully validates the map. And you can do these maps in a way that are very, very easy to create and very, very cheap. And in our case, it costs Waabi less than $50 per mile to create a high-definition map, right? Something that is super scalable, and those high-definition maps can be, updated on the spot, over the air, etc. Right? So you have this ability to be, very efficient, up-to-date, super high-definition, and all thanks to automation. Right? That's kind of the next generation of high-definition maps in the future. Cool. So now we have, this very robust autonomy system, right, that is able to handle many situations, probably safe and all that stuff. But the question is, how do we prove the safety? And how do we teach the system to actually do the right thing, particularly in safety critical situations, right? And how do we prove that indeed the system can actually do that? These are the two questions that we need to answer still. Right? So we have a great brain, but now how do we train the brain? And then how do we make sure that it does the right thing? So the question is typically very simple, which is that if I have this magic wand and I'm able to test the system under all possible conditions that ever is going to experience, and it does well in all those conditions and it does better than a human, then I can deploy, right? I will be much safer and I can actually showcase mathematically with my data that I will be better in the situations that a good human will be, right? So that's kind of the way that you would like to do the safety case, right? You're proving argumentation that indeed you can deploy safely in the real world. Now, the problem of this is that in order to expose this system to all the possible situations, you need a fleet with thousands, tens of thousands, hundreds of thousands, millions of vehicles driving for many, many, many years in order to potentially experience even only a fraction of the things that you will ever experience as you deploy this technology. So in theory, this is great. In practice, that doesn't work. And if you look at the rate of events on highways, they are so rare that you actually see the safety critical cases that is massive what the undertaking into really using real miles. So that's not going to work. So what we did at Waabi from day one was, before we even built any truck or any autonomy system, was we went into this idea that if we are able to create a simulator that can stress test the entire system with the same level of fidelity and realism and diversity that the real world, then we will have that key that, to solve the data problem. And we will be able to not only make the safety case, but also we will be able to train the system on that simulation, right? So that was the idea of Waabi World. And let me see whether Waabi World passes your test. And you're probably, all looking at this, these videos here. It's like, what is Raquel trying to show us here? So I have a question for you to see whether the simulator passes your test. And if you have seen this before, please don't say the answer. But can you guess which ones are simulation versus the real world? Yes.
So the third down, third to the right.
Uh-huh. Why do you think so? Yeah, what is the characteristic that makes you say so? The trees. Uh-huh. You don't like the palm trees of, the trees over here, okay. So a lot of it's kind of interesting, some of the artifacts are actually screen artifacts. I should show you my screen. Any other guesses? I will tell you whether it was or not in a second. Any other guesses? Yeah, it's really funny. Sometimes people say, it's real because it's imperfect world compared to what you see in simulators, right? Some people recognize some areas, like Embarcadero area. It's like, I've been there, this is real, right? So there is many things or many different cues that humans utilize in order to decide, is this real versus not, right? And unfortunately, the screen is not making it justice, but everything is simulation. Nothing is the real world. But it's impossible to say. It's impossible to say for humans, but more importantly, it's impossible to say for machines, which is what really matters, right? Is that for a machine, seeing this is the same as the real world, okay? All right, so this is Waabi World. This is our production system that we use for everything in the company. Every single PR goes through Waabi World, etc. Okay? And so let me tell you how we do this. And I'm only showing you here the camera simulation. We actually simulate all the sensors. Every actor that you see here is an AI agent that lives in a neural world. You get automatic metrics. It's amazing what this thing can do. All right, so, but in order to do this, let me contrast to what you will see or what you typically is used in the industry so that you see how different the design was. And I see a lot of maybe competitors in the industry, so all for you. So what you see here is the three types of simulation that you will see in the industry today. And the first two are the ones that are really used by almost every player or every player. The third one, much less or almost none. Okay? So let me go one by one. So the first type of simulation is what is called log replay, which in my opinion shouldn't be called simulation because you're just replaying data that was collected previously in, with your self-driving platform. And since you are replaying, it's like testing how well you can play tennis by watching a video and then trying to imitate, right? It's very hard to say whether I actually have the right, reverse or not, right? And the same for training, right? This is not the way that you need to experience and have a closed-loop simulator in order to be able to learn how to do this, right? So that's it's very primitive, this type of simulation and the type of testing. The second type is what you see in the middle, which is that you start with representations of the world that are after perception. So you typically have bounding boxes of a few actors, one or two, interacting with the self-driving vehicle. And then you test whether your motion planner is able to do the right thing under several conditions, several permutations of those situations. Now, this is better because you are executing your motion planner, right? So it's actually a closed-loop simulation. But it's also not great from the perspective that you're forgetting about a big chunk of the stack that actually is never going to be perfect. You are testing the system under ideal conditions or very simple noise. So you don't have an idea of whether the entire system is going to ever fail on the road. You only know that under those almost ideal conditions, whether this one module is doing the right thing, right? So that's not sufficient either. The third type is something that is very, very rarely used in the industry today, which is that you create content for a game engine typically, or a physics-based simulation. So you create the content by typically artists that create these three-dimensional meshes of scenes. This is how Avatar, the movie, was created, as an example. And then you use either physics engines or game engines to render the scene. Physics engines are typically extremely consuming in terms of time. So even to render, one image can take, up to an hour or more. And they're also not very realistic in the sense that you still see this cartoonish, it looks cool, but it doesn't, it's very different, the statistics, from what you will see with real world sensors. So this type of, but you can create synthetic data, and this type of approach is used only really to help train perception systems for really rare things. For example, emergency vehicles is one example that I think Cruise show. Okay, so very little use, very big domain gap, simulation doesn't look the same, etc. So there's a big hole in the industry in terms of creating these simulations. Okay, so but we are after something that is not trying to test just sub-pieces or, but we're really after mimicking the real world. Can we build a simulator that is going to be realistic, controllable? You can simulate everything, it's fast, so you can run billions, trillions of simulations. It's going to be reactive so that as you are driving, everybody is reacting to you, right? The same as humans will do, or animals, or whatever it is in the simulation. And very importantly, provides you feedback. What does it mean is that it's going to score you for everything you do. And it's going to score you in many ways so that not only you will know whether you're doing well or not, you're also going to use that signal to train your system. Right? So you need trustable metrics that then you can use to learn to actually perform better and better and better. Okay, so now you're going to have two AI systems that interact. They're very different. But one is the teacher and the other one is the student. Okay? So let's look at under the hood of how Waabi World works. All right, so given a simulation, and I will show in a second how we can specify this, the simulation is going to mimic the world. So it's going to have a representation of the world. That is a neural representation. It's a very complex representation, okay? But, we have the self-driving vehicle in that environment, right, that is driving around, and there is many other agents that are also living in that environment, okay, for every single simulation. So at every tick of the simulation, we will do the same as what happens in the real world, right? So in the real world, you're driving, your self-driving vehicle is sensing the environment, right? The cameras, the radar are seeing. Given everything that you see, you're gonna execute the entire stack. You're gonna decide on your actuation, what it has to do, right? The steering and acceleration, etc. And then typically in the real world, when you tell the system to do a particular maneuver, what happens is that in reality, that's something a little bit different because there is several perturbations. There is wind, there is things such as the fact that you have gear changes, you have friction, ice, whatever it is in that environment, right? So there is some deviation, and then given that as the reality, then this loop continues, right? While everybody in the world, all other people, etc., are also living their lives and reacting accordingly, right? So that's the real world. So what we build here is the same thing, but with Gen AI submodules. Okay, so we're gonna simulate how the sensors observe. This is the stuff that I was showing you before. We're gonna be able to run the entire autonomy stack on simulation. We are gonna also be able to inject learn latencies so that you can also see your reaction time and whether you're gonna get in trouble if your compute is too slow, etc. And we're gonna also learn the dynamics of the world so that you get all the perturbations as well for free. Okay, and at the same time as this is running, then we will run all the AI agents so that they have their goals and they are driving around this world, including, as I say, animals and other things, right? So, and we run this in a tick, every fraction of a second. So basically, you have a way to really recover and generate the same way that the real world actually works. Okay, and without Gen AI technology, none of this was possible. You will never get to the level of fidelity that I showed you before. Okay, so this is how Waabi World works, which is very different from any other simulator out there. All right, so let me show you how we actually generate the content as well. So we're going to do this by cloning the world. And the idea is very simple, that if you can clone everything that you see and then put it in a catalog and then reuse it afterwards, right, you will have the ability to simulate almost everything. Just by being in this room, there is hundreds of people here. I have hundreds of yous cloned in my world, right? And then I can clone you to do all sorts of things in the real world. All right, so on the left-hand side, you see the real world. On the right-hand side, the simulation. And what we are doing is we are changing what the actual scene was. So you can clone it and you can modify the actions to create counterfactual what-if situations, for example. You can, regardless of how you capture that world, you can render that world from any perspective. This is the way that we can train autonomy systems of trucks, sensors that don't even exist today. And you can do this in a way that is, very, very scalable and very, very realistic. You can drop different agents here in that world. They come from a different part of the country, and they can actually experience, a different place. And you can transform, all the actions and everything in a way that is composable, etc. Right? So it's a super flexible framework where you can take anything that you ever observe and create new things with that. Right? And this is a concept that if you can do this automatically, as we do, right, everything comes for free, super, super scalable and diverse, etc. And you can do all sorts of different, times of the day, different weather conditions, and things like this. Okay. So this is our answer to the data problem, right? And now, since it's generative AI, you can generate anything out there. All right. So the cool news is that you can generate anything and you can test anything, meaning that you can specify your vehicle. You can specify your software stack. You can specify the hardware computer that's going to run on. You can specify where your sensors are, etc. So not only we can test Waabi's technology, we can test everybody else's technology. So this is the ultimate driving test for any self-driving vehicle. And this is something that actually regulators are very excited about potentially be able to use to certify systems, not just Waabi. Now, in terms of generating that content, so what we can do is we can generate composable, modifiable clones. I show you a whole bunch of videos, right, that actually showcase that. We can generate totally new content with our generative models. The user can actually create through language. We have a simple version of it, and we are looking into a more sophisticated version now, where you can actually create very specific tests. This is for system engineers, safety engineers. They want to really test particular things of the system. And we have this really, really exciting mode, which we call adversarial, where basically the simulator optimizes for the software stack to fail. And why is this important? Is that you want to understand what are the deficiencies of the system. What is Waabi driver or the system under test not able to do, right? And the simulator can actually automatically change and evolve the scenario so that it's harder and harder and harder for that particular software. So you can automatically discover all your corner cases. Amazing, right? And since you can discover the corner cases, you can generate those examples and you can train on those and become better and better and better. Okay, that's the way that you can really learn very efficiently in simulation as well. And you can have combinations of this. This is all composable, etc. For the agents, I think it's worth mentioning that we have many models. The reason why is that you don't want a trained Waabi driver to be good with respect to a single type of human. It can be for anything, no matter whether you're distracted, whether you're drunk, whether you are adversarial, or you are a nominal person. Okay. We can also prove the realism of the simulator. Stay tuned for how we do this. And you end up with this tool that basically covers all the desiderata, all those requirements that we have for the first time in the industry. Right? This has been a massive unlock for Waabi, where we also optimized for our hardware before we even built it. That was one of the examples of what you can do with this. So this type of simulation really enabled us to do most of the things on simulation and use the real world mostly for validation. Right? And that really flips the pyramid in terms of how this, the information that you get out of simulation versus real world models. Just maybe one or two sentences about our hardware. We integrate sensors and compute, and we have a model that is built upon building things that you can integrate at the factory line with an OEM so that you can build this reliable product and safe product at scale. So it's very plug and play, lightweight. If you're in Texas, you can see our self-driving trucks driving around, and it's also very flexible. For example, we don't need targets for calibration. The system can calibrate itself without any requirements for the environment, right? That's something that, it removes a lot of the friction that you have today. Maybe a few words about safety. So safety is very important, and it's important our definition of safety. And oftentimes we talk about safer than a human, but that's just one bit of it. Self-driving vehicles have to drive responsibly, which means that not only we want to improve the safety of us driving, but the safety of everybody around us. So we want to improve safety for all, and we want to be able to prevent situations so that the probability of something happening is very, very low. So it's not just about preventing collisions, but also preventing getting close calls, for example. We want to be minimal disruption, right? You don't want to, for example, interfere with emergency vehicles. You want to be adaptable to changing conditions. If for whatever reason you don't see well, it's important that you drive slower. You want to be able to respond to the unknown, as I mentioned at the beginning, right? This is very important. And last bit, I want to say a few words because this is something that is very important and puzzles me, maybe some of the statements out there, which is that being compliant with the rule of traffic, we should, but there are some situations where you should not. Okay, so hard coding rules of traffic is absolutely not the safest thing to do. And let me show you an example of why. So here's our truck driving around. And you don't see what's going to happen, but there is somebody that for an emergency stopping lane. And with a truck, it takes time to really be able to brake. So we couldn't just brake and have a collision. And on the left lane is full with somebody else. So we can't change lanes. This is an example where you have to not follow the rules of traffic in order to avoid an accident. Same with a red light, same with any rule whatsoever. So safety should always come first. And this is very, very important no matter what. Cool. So in terms of safety, and there's a few folks in the room here that do VMV. Very important, the standard methodologies that are available in, I will say in the industry today, but they are not sufficient. They're not sufficient because they don't cover the diversity of things and scenarios that are going to happen in the real world. So you need to go to a statistical approach. Formal methods also are not able to, we are not able to prove things given the uncertainty and the failures and whatnot of the system that you can have. And this is why just driving on the real world is not enough. Hopefully I convince you with the rate of events. Death on the road is every 100 million miles. Bodily injury that is severe is every 10 million miles, right? You can't drive all that and you don't want to create those in the first place, right? So we need a closed loop simulator, and then Waabi World, what I showed you before, is the only way today to provably save and assert the safety of self-driving systems. Cool. So I show you these two systems, right? You have Waabi Driver and Waabi World that enable us to provide a brain for our self-driving vehicles so that they can, it's a single AI system, it's end-to-end, but the generalizes, it's efficient, it's provably safe, and it's interpretable, which is very important. In the last 2 minutes that I have, I will show you maybe a little bit about where we are with the company. So I founded Waabi in 2021, so 3.5 years ago. And the first thing that we did was we launched the simulator, right? So that we could start working in autonomy. We could start deciding what is the best composition of sensors for our hardware, etc. Then we went to public roads in May of last year, and since September, we've been driving commercial loads on public roads in Texas with some of the largest shippers in North America. Where are we going? The system that I show you here has amazing generalization capabilities. It's something that I have never seen before. For example, the first time that it ever experienced rain, it had no training data, no nothing, and it was able to handle it perfectly. As you work on this domain, you know that this is like, wow, right? That was the aha moment for me. This is why we are very confident on our driverless launch next year without a human. Cool. Other things is that it's very important. We have an amazing team behind Waabi. Some of the folks are actually sitting over here. So please, after this, talk to them. We have the right technology, but we also have the right investors. One of the very exciting things that have happened recently is we just closed our Series B financing, the largest in Canadian history, with over $200 million. And the $200 million is great, but it's not the important bit is actually who is behind Waabi. As you see over here, best in class in terms of AI, logistics, OEMs, financial groups, as well as the thriving Canadian ecosystem. Cool. So I wanna leave you with a thought, which is we talk a lot about self-driving trucks today, but everything I show you, the brain and the simulator, there's nothing inherent about trucks on it. So we can actually utilize this technology and be able to do other form factors really, really fast. Now we are very focused on self-driving trucks and launching our first product and having a path to scale, which is coming very soon. But you're gonna see much more from Waabi. This is just the beginning of an amazing transformation of the physical world. And with these words, thank you very much. It's all from me.
Okay, let's see if this is working.
Yes.
Okay. Thank you very much for the fascinating talk. I will humbly introduce myself. My name is David Ramanan. I'm a professor in the Robotics Institute. And I have the good fortune of moderating the question and answer period. So I think there is a QR code for folks that would like to submit questions. And I also want to call out, there's a virtual audience of around 100 folks. You're also free to submit questions as well. And I will try to kind of shift between those and my own questions that I'm eager to ask. Okay, so maybe I'll just start off with one that I wrote down. So it was very inspiring and compelling to see this vision of building simulators and as world models to help deal with this data problem. And I could imagine that if one of the goals is use that to help address this safety critical question of maybe validation, that at some level we also need to validate the simulator itself. I'm sure you've thought about this, so I'd love to hear your thoughts on that.
Yeah, super. Great question, Deva. So it's very important that when you have an argument for your safety case that is based on simulation, that you're able to prove that that simulation is realistic. And this is also for everybody, right? It's not about how many simulations you run. It's about, are those simulations actually having the same fidelity as the real world? So what we can do with Waabi World, because it's grounded on digital clones, we can actually validate and verify the simulator for the first time. And not only we can do it at the level of every component's fidelity, but we can do it at the outcome level, which is what really matters. And we can prove that driving on the simulator under exactly the same situations and conditions and appearance and weather and everything, under, on the per setting, you will do the same on simulation as you will do in the real world. And that's the ultimate argument for validating and verifying the simulator. And that's what we can actually do. Yeah, great question.
Fantastic. Okay, so I'll take one from the online forum. I'll just read it out loud. So may I know how important you feel scaling and search are to future developments in AI?
Scaling and search. So in terms of, I'm going to take the scaling as a data scaling variant. And I don't know whether the audience, the person in the audience is what they had in mind. But, my philosophy has always been that it's not about quantity of data. It's about being able to select the right data. And for every data point, you should have as much information as possible that helps the system learn. And that's what you will see with the type of approach that we have, right? Where not only you have an infinite data set, you can choose the example at every bit that gives you the maximum information gain. And that's the way that you can actually do training very, very efficiently. And in Waabi World, you know everything. You can assess whether you're compliant, how the risk of that specific as you are driving, what you are doing well versus not, if you're perceiving your abstractions are correct. So you have at all levels supervision for free automatically, right? So every one of these examples is like super informative, and that's kind of like where we have gone, which is very different from what you see on the LLM world, which is all about give me the entire internet and give me, a data center with the power of New York, and then I will train this thing. And now we see that they are going more and more in terms of curated data, right? So we went on the opposite extreme, and has been extremely important. As it relates to search, one of the things that we also use Gen AI for is that you can query your logs, the things that you have already driven in the real world, for specific things that you might be interested in. And you can do this in a free-form manner. That's an example where new versions of search are very, very important. Hopefully that's the kind of search that you have in mind, whoever you are online.
No, fair enough. So I'll continue with another question that I also had in my mind too. Do you have any sort of comments on the role of sensors? So you clearly showed examples with RGBs and LiDARs, and clearly there's well-known companies that are betting on certain sensors versus others. And what is your view of that, and how it relates to the data question?
Yeah, great. So sensors are obviously very important, right? And one of the great things about starting a company in 2021 is that we have a second mover advantage. If this was 2017, I would say we need to invest into building our own LiDAR, for example. Today, there is a couple of pretty exciting products that have a path to scale and be automated graded in the market. With the type of technology that we have, we can handle noise of the sensors, for example, and we train with by simulating noise and other things that makes it extremely robust. And the other bit that I will add is that we don't need FMCW LiDAR because the foundational model is able to really understand motion really, really well. So we are in a fantastic spot in terms of what is available in the market. And the other thing that is very exciting is that when a new sensor comes to the market, we can, with just a tiny bit of data, we can create the ability to simulate that sensor in all these situations that I showed you here. So we can actually, before you even mount that sensor, even on a truck, already have the autonomy system ready to use it. So that enables you to be super fast also if something comes that is very exciting. So I think we are in a fantastic spot given all the advances of sensing that has happened, our ability to get new sensors and move forward.
Okay, so here's a couple of fun questions. How do you accommodate regional differences in driving? Boston drivers versus Pittsburgh drivers.
Pittsburgh left or whatever it's called. Yeah, I guess that's very basic here. Yeah, so I mean, one of the things that you can do is kind of incorporate in the model, learn to have certain preferences. And it knows what it is in the world. And it knows, potentially you can make distribution of what you expect people to do to be dependent of where you are. So that's something that you could do. We don't do this today, but it's something that you could do. Or you can just build what is our approach, a robust model where no matter what the behavior of other folks are, you're still able to handle. But if you want our trucks to squeeze before everybody else on that left, then you will need to have some geocode in there, which is very simple to do, by the way. Yeah.
All right. Okay. Let's see here. Oh, there was, this question I thought was really fun. So in general, this is more of a philosophical one, I think.
Now I'm scared, yeah.
When you're incorporating essentially Gen AI and machine learning and autonomous driving, and maybe even more specifically perception, what is the most pesky problem you encountered?
I will say that, if you go with mainstream Gen AI, that stuff doesn't work. and doesn't work to the level that you want for the task at hand. So if you want to take an LLM and fine-tune it, or multimodal LLM and fine-tune it for this task, it creates great papers, but it's very far from something that you can deploy. You need to build different, or our lesson learned is that you need to build very different architectures that really more tailored to this problem. And then that was an important design, but of what we did, that if you don't do that, is going to be extremely hard to get to a safety critical system. And then how do you validate this? But it's not trivial, all the stuff that we did, right? Like we went with kind of the opposite approach, say, and we invested heavily on the simulator and building this. It was a lot about bringing a research mindset while building a product, and that was not trivial. And how do we built Waabi's DNA on that, which is, in itself, something very complex to do that very few companies have been able to do, to kind of like crack that nut. So I would say there was quite a few complications, but we are in a point now that, we are very excited and confident about the path that we are moving forward. But I would say that this marine research and innovation was extremely important, and they just have, really faith on our path being the right one, and hopefully it wasn't wrong for 25 years, and now finally we can see this.
No, fair enough. Actually, so to kind of riff off of that question about translating innovations and machine learning and AI and Gen AI, I could imagine that if we think of, one of your first slides showed off that, very dramatically that ChatGPT has had a more rapid period of adoption than almost any of these other technologies. And so clearly something really interesting and transformative has happened in the space of language. And maybe one of the prevailing sort of wisdoms is that scale is one of the key enablers there. So, we can train on trillions of words. And so I wonder in the pipelines you're envisioning, to what degree, I know that sort of in order to achieve that level of scale, I think one of the unique perspectives you have is that simulation will allow you to get there. But I imagine that another pipeline could be trying to use other sources of information, like what you already suggested, trying to almost learn from this huge collection of words. Is there any useful knowledge or common sense knowledge that can help you drive, or learning from image collections online or video collections online? And because my impression is that might dictate one sort of your choice of sensors, because so for camera data, we have lots of other data you can find that you can learn from at scale. So any thoughts on sort of transferring information from other data sources?
Great question. And we have a lot of language, a lot of video and camera data. We have very little LiDAR data, for example, right, or radar data compared to the other sources. But I just philosophically don't believe on build a trivial algorithm and just scale the data. Okay. I just don't believe on that. Like, I don't think that's, I'm obsessed with efficiency, and this is maybe, my, maybe a problem in life. But I would say that, it's very unsatisfying, this idea of, yes, give me more data, give me more compute, and yes, the course will continue, and one day we will arrive to the bottom, right? I think that we can use the brain power that we see in this room and across the world to come up with better algorithms, come up with better architectures, come up with better ways to generate the data, etc., that will enable us to have a much more sustainable approach. Otherwise, these days, training one of these models is over $1 billion. And if now you add other modalities, and some of these modalities are more expensive, like what, where are we going? So I would say that I rather, believe on the, or do things on the other camp, and is potentially harder to get to a certain level, but I think you have really a much better path to the end.
Got it. Okay.
But it's very contrarian. That's these days in particular.
No, it's cool to hear that positioning. Yeah. So all the people working on scale should be running away from you. But it is really compelling, particularly the kind of the argument for like efficiency and sort of like wastage of energy and compute.
Like one data center is the power of New York City.
Yeah.
Just think about that.
Maybe kind of to continue with the, I guess one of the avenues for efficiency is being able to control and generate your own data via simulators. There was a question that also popped up of to what degree it seems like the simulators that you're showing, it's some combination of, it's almost data-driven simulators. So you learn from real data how to re-simulate and put things in different places. And so there's some element of injecting knowledge about how you can re-simulate things, and there's some element of learning from data.
Yeah.
And so there's a couple of questions of to what degree should something like physics be injected, or to what degree should it be learned from the data?
Yeah, great question. So our philosophy has been to build architectures and things that are physics inspired, but they're more powerful than physics themselves. So that's the way that you get, and Nerf is an example of physics inspired with, very powerful that, that you can do some really cool stuff these days. So that I think is a very, very interesting and powerful approach. And in Waabi World, that's the kind of thing that you will see. Like physics is very hard to simulate an imperfect world. And the world that we live in, there is so many phenomena and things happening that actually influence what you see, that you can't really, it's impossible to know everything about the environment and simulate perfectly and in real time, at that scale, that's just not, just too hard, right, for us humans. So with the approach of, don't forget about all that, very interesting stuff that has been developed over the last, decades, but take that knowledge to build this marry between physics and AI and in a single model. And I think that's extremely powerful, and that's the kind of approach that we're doing.
So one concrete example there would be, for example, like weather conditions. You mentioned that one of the cool aha moments was seeing it generalized to rain. And so right now, do you think rain is easier to inject via just data or actually simulating?
Yeah, so in physics simulation, typically what you do is that you simulate every single drop of rain. Just think about that. And how hard that is, and how time-consuming that is in terms of all the computations that you need to do. And do you know everything about, the atmospheric conditions that you have and how it's gonna, all the different physical phenomena that you need to simulate and how they affect everything, and those rays bouncing around and whatnot. So it's impossible, right? So I think that's a very hard path that is not going to get us to the fidelity that it is. But AI is very good at faking things that look realistic, right? So through physics, you can get part of it, and then the noise bit is where AI is very good at. And that kind of it's not exactly that, but that kind of design typically works pretty well.
Got it. I think we have maybe time for one more question. I'll take one that also kind of bubbled up, which I think is also a fun one to end on. I was struck by your slide where you pointed out that it's not enough to be safe, you have to be provably safe. I think it was sort of articulated really nicely. And here's a question that sort of riffs off of that. So you talked about two aspects of provably safe. And so one is being statistically safe in simulation, and the other is being more explainable or interpretable. And so which do you feel is more important?
The first one, for sure.
I see.
For sure. And the second one also helps achieve the first one. Statistically proved safe should be sufficient.
Yeah, and so
even if you have a black box architecture, doesn't matter. It's just harder to do, right? On that case.
Got it. And would you say that you think that can still be done via simulation, or does that have to be real world?
It's impossible in the real world. It's just impossible.
I see.
Right, with the rate of events I was talking about, it's just, nobody has fleets of that size that you will observe that. And you don't want the risk, like every time you think, my system is ready, and I go and test, and oops, I had all these accidents, but I was almost there. Let's try again, right? So I mean, I'm kind of making fun of this, but it's, that's not the way that you can get there. So simulation is an absolute must. It's the only way to do this in a safe manner, right? Yeah.
Okay.
Anyways, yes, my opinion. Yeah.
No, I buy it. I buy it. Convincing argument. Maybe we'll conclude with our Q&A. We'll thank Raquel again.
Thank you.